Hello, everybody. So, looks like we made it up to Module 8 last week of the semester. We hit all our major learning objectives. So, this week there's just some odds and ends. I have a rather large list of odds and ends. We won't go through all of it, but usually at the end of the semester, I like to throw things out that I believe will be useful for you all, either on your way through education or in your working careers afterwards, and things that might be skimmed over briefly in courses or not show up in courses altogether, which is what I wanted to talk about tonight. A little thing about graphics. As far as using graphics, I think everybody already knows what to do with them, right? Go search for the picture you want, download it, and as long as it's not in that new format, search engine started putting things in, you just upload it, insert it right in where we're going to use it. And we don't really look at the difference between them or anything. But there are some differences, and sometimes I don't know where everybody's heading in their future careers, so you could be heading in a place where the differences between the graphics do make a difference, but it's not covered anywhere. Even the graphic design people don't really study the difference between the formats, how the data is stored internally. So I like to cover it somewhere if there's time, and we have time here, so I want to look at some of that and the difference between the pictures. What I put in my notes here. So the old saying, the picture's worth 1,000 words. People want imagery, not descriptions. We had a discussion board a couple weeks ago about graphical representations of data. In the fall, there is a class DBMS 160 that we'll be running, which is specifically the visualizations for data sets, going over that. I think they're going to use Power BI in it. More than just insert a chart. So really dive into that really deeply. See lots of charts and more powerful software, things like that. So that class is running in the fall if anybody's interested in that sort of thing. Very, very useful. It's a data analytics course, but I've been kind of trying to promote it to business people because they're definitely going to have a need for data visualizations. Nobody is going to take the time at a Tuesday morning meeting to look through an actual table of data. But people want imageries, not descriptions. Storing image data in some sort of binary encoding obviously proved a little more tricky than those alphanumeric numbers we looked at when we talked about binary. Our brief introduction to binary, we saw the numerical representations and then did a one-to-one encoding for ASCII code, which also happens to be the first 256 characters of Unicode. So the way we represent our symbols, we just say add an extra bit on, and if that bit's true, then we're looking at a number. If that bit's false, we're looking at a character. Very straightforward, but graphical data is a little bit different. But people are very creative and persistent, and they came up with a lot of solutions. And in general, for usage, we're just going to find the image we want and insert it into our Word document or slide deck or whatever we're going to do with it. But there are some differences between them that you might need to know, and it's not covered anywhere, so I wanted to look at that. So first thing I'm going to do is go ahead and draw a picture here and put a couple different formats at it and see if we can open it up in a form we can look at. Probably should have shared this link with you. I'm going to open up this software called Inkscape. This has become quite popular lately. It's open source software, so we can get to the source code and customize it if we need to, write plugins for it in Python. It's the open source alternative to Adobe Illustrator. The difference between this and Adobe is it doesn't have the CMYK, so it doesn't print so well. It only has the digital color, which might be a little point to start off with here on the lighting. If you want to follow along, you can just search for Inkscape, INKSCAPE, kind of like landscape thing. It's open source software, very powerful graphic software. Has a lot more functionality than what you might be used to. In particular, it does vector graphics, particularly two-dimensional vector graphics. But that's like the fourth thing in the notes. So we'll get to what that is in a moment. But I just mentioned that the difference, big difference between this and Adobe Illustrator is Adobe has the CMYK colors, which by the way, cost extra on top of your subscription anymore. Do y'all remember back in elementary school when you learned art class, like kindergarten, maybe first grade, they're showing you how to mix colors, and they say mix red, yellow, and blue to make any of your colors. And then other times you hear mix red, green, and blue to make colors. So the difference there is it's different types of light, because there's two ways we could see some light, see something. So we have some sort of light source, like a light bulb here. And oh no, I'll just draw like a table. And we want to look at this table. The light could come from the source, bounce off the table, and then reflect back into our eyes. And that's what we see. So the reflected light whenever we're looking at reflected light, before it bounces off, certain wavelengths of light, certain bits of that light get absorbed. So it doesn't bounce back, and we don't get all of it after it bounces off. And to get reflected light, that's what you learned in like elementary school, mixing colors. It's actually magenta, yellow, and cyan that we mix. But we usually teach that to kindergartners and first graders that probably don't know what magenta and cyan are yet. So we just say red and blue for those. Alternatively, if this light was tinted, like the green LED light or a blue LED light, something like that, we could pick up that light directly into our eye, the source lighting. And source light is a mix of red, green, and blue. So this open source software I just mentioned, it's missing the CMYK. I wrote them in the wrong order here, but cyan, magenta, yellow, and K, usually for black. If we look at it on the screen, it would be more of a clear, because we're turning things off to see black on a screen. And on a laser jet, it's clear, but on an inkjet, it's black. So the K stands for different things. That's why they didn't go with the B for the black. But that's what we need for the printed version. So Adobe Illustrator, if you're going to print stuff out, you want to go with Adobe Illustrator, but most things these days stay in digital format, right? So this has become very popular lately. It does scalable vector graphics, and I'm going to just do a quick picture, and then I'm going to save it in different formats here. If you need some graphics software, this is some nice ones. This is what I use most often with my pen. I'm going to erase this part, but I can just grab the pen and draw a bunch of stuff here like a stick man. And this is just to show that you could do all the fancy stuff, but notice I can still get back to any particular one. A lot of graphics software, once we draw it, it's drawn, and we can't get back to it. So with vector graphics, we can still access any one of them and things like that. I'm going to do a very simple picture here that we can refer to and that I can copy onto the board at times, talking about what's going on inside. So I'm just going to do, I guess, like the basic picture. So I'll choose some blue stuff here for the sky. Looks like sky color. I'll fill that in and stretch it out to the right size, or put it in place, and come in here and do all the editing, like turn off that outline. There we go. And that fit about where that is. Stretch it out longer. There we go. another rectangle down here for green, for the ground. I'll just select that. It's not a fancy picture. Don't need to spend a lot of time with the picture. Maybe a rectangle here and make that brown. Which is an interesting thing about expectations. Everybody knows the tree bark is green, right? Or tree bark is gray. But if you draw tree bark gray, people think it looks strange in an image. Even though we all know that that's the color tree bark would be. I'll do that, and maybe put the sun up here in the sky, make that yellow. And we can still access any single one of these, grab all the pieces, move around where they need to be. It's all stored separately. I'm gonna get a regular blue instead of fancy blue. That'll work. So nothing fancy about the picture. That's not necessarily the point of it. When I hit save, notice the type is .svg. So that stands for Scalable Vector Graphics. We will get to those here in a few moments. Delete folder, I'm gonna make new folder. Thanks. And sure, I'll just call it drawing.svg. That's a good name. I'm leaving this open. There's some advantages. So like, if I wanted to animate this, I only have to draw it once with the vector graphics. With pings or JPEGs, if I wanted to do an animation, I'd have to do every single come back and draw every single frame. With vector graphics, I can just draw it once and then tell the computer how to move. We'll talk about that soon. And to get some other formats to look at, I'll just use Paint. I'll open Microsoft Paint and open that and save it in different formats. Oh, wait. Actually, I can't open SVG graphics in Paint. Let me do this. I go back over here, it's saved, so I can export that as a thing. They're in the same folder, so then I have so the same image, but so far as a SVG and a ping, and I can just use Microsoft Paint has options to change the format, so I can switch that into JPEG. Let's keep the same name. It'll lose transparency. That's an important thing. Since I tried to, Microsoft Paint does not even support transparency. But as soon as I tried to save it as a JPEG, it said you're going to lose any transparency if you do that. Little differences like that. I think you can go to a bitmap from here too. So I can then go save as bitmap. If that'll work. And before making any other changes, I can also save it as a GIF. And here's another message. When we go to save it as a GIF, we get a message. The color quality might be lost, which we can look at this picture. Obviously, the computer can't analyze the color quality. There's not much we have to lose from that quickly drawn picture there, but we still get that automated message that the other format doesn't have as good as quality as the one we were just saving it in. Oh, where those say that? I have no idea where I just saved those. There they are. I'm going to move them back over to the proper. So they're all in the same place. So the thumbnails almost all look the same. The pictures, if we just open them, most of these are going to open with the photos, or thought they would. Open it with the Photos app, no matter which one I open it with, they're going to look the same. This one, wouldn't open with photo apps, but I can open it with the browser. And all the pictures look the same, because we didn't adjust color quality or anything. But there are some big differences between them. And to see those differences, I'm going to go to Super Basic Text Editor Notepad and open them up here. So we first drew it as the SVG. We're going to look at that in a moment. But if I open the SVG version, look at all the files, you'll notice that it's very readable. I remember back in module 4 or 5, we did the software development lab and there was some HTML stuff to do. Hopefully that kind of looks familiar with the HTML. We have those tags everywhere, like we did in HTML markup languages. And it's all human readable. That's one really nice thing about that. I'll talk about what this stuff means here before too long. But we can see it's all in human readable form. Oh, nice. I have tabs in Notepad. I didn't know they made that update. So if I open another one, which I should probably do in a new tab, here and open select all of them. Can I open them all at once? It says it has tabs. There we go. Able to open them all at once. So the SVG, it's all human readable. We can see what it is, which should be an immediate indication that we're not looking at what's actually stored. We're definitely, what's actually stored is binary code. And so there's an abstract layer to get to here so we can get it into human readable form. No picture there. And so this is the bitmap. Yep. Notice right in there at the top, we can recognize BM. That's how I knew it was a bitmap. So it's spelled that out. And as we look through here, there's some random symbols where the computer was trying to put it in text format, but it couldn't really turn that code into text format. Then we have this long thing that repeats. Let me turn, I'm turning WordWrap on. So these lines are at, we have a whole bunch of repetition. Looks like most everything is the same. It couldn't accurately portray it in text, but it tried. It's like, okay, if here's a group of 16 bits, so if I turn those into Unicode, it'll make these symbols. It's not really the right thing, but we can see there's a lot of repetition, then a little bit of change there at the end, some other information, and then once again, we have a whole bunch, a big, huge repetitive section. Then a little change at the end. And then we have another big, huge repetitive section and a little change there at the end. So we can see that there's large repeated sections forming and patterns. So that's on the bitmap. Here's a GIF, however you want to pronounce it. We'll talk about that in a moment. This one kind of looks like a whole lot of gibberish. The file's a lot shorter. There's some repetition, not as much as the bitmap had, and then it looks like a bunch of gibberish, but a much shorter file. And if we look, we would be able to find some repetition in these patterns, but obviously that's staring at abstract things kind of, we're not going to make any sense out of it, but there's a lot of repetition there. The JFIF, we can recognize those letters. Some other information before it, but this is the JPEG one. And scroll down, looks like it tried to get some symbols out of a few things. Couldn't really do much. And if we scroll down, there's this short repetitive section. Where does it start? So we get that short repetitive section. Then we have some change. Then we have a slightly different repetitive section of about the same length. That'll be important when we talk about what JPEG is. We have some other stuff, and then we have another repetitive section that actually looks like the first section repeated. As we scroll down, we will see that same thing over and over and over again. So here's the same thing again. And this is like that other one that there, and then some other information about them. And as we scroll through here, there's not large sections repeating. There's these little lines, like this a little bit repeats. The symbol repeats a few times, but then it moves to something else. Then a whole bunch of what looks like randomness, and then at some point later we'll get this repeating section and back and forth, and we'll see the same things repeating over and over again. And it's also a very long file. Notice it keeps scrolling and scrolling and scrolling on this one. And there's not really many patterns repeating or anything. So the way that the format, we can see that something different is going on inside there. And a ping, so we have this section at the beginning, then it looks like a bunch of randomness. And scrolling through there, it's shorter than the JPEG. Looks like a bunch of randomness, but I don't really see any repeating patterns. Nothing more than a few symbols at a time. So the way it's stored, and then we get down to this large bit of information down here. So now we're into some repeating stuff, but not much. And a whole other, then some repeating stuff at the end, but we can at least see from this format that they're all in very different. The binary code for each individual one is very, very different. So I wanted to talk about what those are. It's the same image stored in different formats. So first one, erase that. I always like to work that in somewhere too, because it often confuses people why they hear about the different colors. We're computer people. Obviously with the monitors, we're talking about source light. It goes right from the LED straight to our eyes. Or I guess there's other sources. In 2023, it's all LEDs or OLEDs. Not many LCDs left. Very few cathode ray tubes left. But I guess other sources do exist. But it leaves people curious why it's different than what their elementary school art teacher told them, because that worked too. The Solo's mixing. So the first type, let's look at a bitmap. Or usually like .bmp is the extension. This is a collection of instructions about what each pixel should be. Collection of color instructions for each pixel. This is what most people probably think of when they think of the think of computer graphic data. We have this big table. I hope this marker holds out. Is this showing up on the video? Hopefully. No, probably not. But we have this big grid. Each cell in the grid represents a pixel. So if we're on our picture here, there's a lot of blue. Where do we have? Blue, yellow, green, brown. I'll use B for blue and a W for brown, so we can do it all in one letter. But we had a whole bunch of blue pixels. Blue, blue, blue. Over here, we had a bunch of yellow pixels to make that the sun. I'm going to do it like this because I'm limited on space. Surrounded by blue pixels. Somewhere over here, there was some green pixels for the tree. I'll use a W for brown because that way it can all be done in one letter. Then down here, we had a whole bunch of green pixels for the, I guess, grass. And then everything else was still a blue pixel. So it looks something like that, which is probably what we first think of, is related to the LEDs. Turn this pixel blue, and then this pixel over here turns yellow, and we adjust each particular color. Not necessarily how relating to the screen, because this is how we store the data. This is what we would also send to the printer or to a projector, which is a projector uses reflected light, not source light, or different things. We would. This is how it's internally stored, but most people think of this because it relates nicely to the screen, and that's why we had all that repetitiveness in the bitmap version. Where all those blue pixels, it just repeats over and over and over and over and over again. Then we hit a section of yellow pixels, and all those repeat over and over and over again. And we get the instructions for each particular one. And the important thing is that where this would apply is when we scale the picture. Y'all have probably seen it before. If we scale the bitmap up, it's going to get pixelated. But we can scale a bitmap down and still have some clarity. Because if we dropped every other pixel, if we dropped every other row and column in our grid, we would still have a lot of information about pixels. So if we make it smaller, we don't lose anything. But if we make it smaller and then bigger again, we dropped half of our pixels. So then it gets even more pixelated than if we would have stretched it out to begin with. Y'all have probably seen some of that stuff, right? But the pixel by pixel instructions. Next is Joint Photographic Experts Group. The blue marker gave out on me. Let's see if the black one works. Okay, that might be one that was making noise. Let's see if the green one works. Everybody see that? Color coming through okay? Joint Photographic Experts Group. So this one is named after the people who invented it. So .jpg or .jpeg, usually said JPEG. There's plenty enough there to pronounce it. This one's a little more complicated, but to try and talk about what it is, color data is stored as a discrete cosine transform. So, a bunch of words there that come from mathematics and quite possibly higher mathematics classes than you all have had if you're in a 109 class with the number 109. So I'll start with cosine. So cosine is a trigonometric function, really the stuff about triangles, but it also describes circles and waves. In particular, we want to think about it as a wave. There's two main types. So there's a sine wave that starts at 0, goes up, and comes down, and back up. That's referred to as a sine wave, and a cosine wave starts at the top, comes down and back up, and then just repeats from there as we have a wave that keeps going and going and going. So we end up with a bunch of the crests and troughs like a wave. Discrete, it can mean different things. Discrete is like what we have in a computer, ones and zeros. It's one or the other, and we don't have anything in between, like that on or off. Our voltage is never exact as far as electricity goes. So we set a threshold, and then we are either above the threshold or below the threshold. So it's discrete, but in this case, it's referring to those waves, and sort of we restrict it to, instead of any possible waves that would fit in our box. So the cosine waves, so they start at the top and come down and finish there. So that one fits nicely in the box. But if we had one that came down and up and down and up a lot, I got a little off on the picture, but that one would also fit because it starts and stops at the correct spot. One that came up and down and up, and this one would not work because it doesn't fit in our box. It has the wrong start and stop point, like the sides of the wave don't line up. So discrete is in, we restrict it from every possible value to a finite set of values. And transform refers to what's known as a Fourier transform, where we put several waves together. Maybe we have one that's kind of spread out like that, and another one that has a lot more troughs, and then one really slow moving one. We can put those together. So the high parts add together and the low parts cancel out. The high parts and low parts add together, and those are like positive and negative values. So the positive and negative parts add together and cancel out. So like up here, all of them start at the top, so it's all very positive. And this one drop down, but this one's still up. So it doesn't fully cancel out. Then this comes back up, but then this one's still down, this one's up. So it tries to jump back up, and we add those parts together, and I'm not gonna do the whole thing, but we end up with a different looking wave that more like what you all would think of if you saw a picture of a wave, like a sound wave with lots of jagged edges, because we took all these different things and added them together. That's what the transform means. So we have a bunch of different waves and kind of put them together. I drew them backwards to be somewhat realistic. This would be like the red wave. This would be like the blue wave. And this would be like the green wave. And then we add those positive and negative values of red, green, and blue together to get something. If we looked at the picture of it, it would look like a sound wave. When we add all the different waves together. That's not a very good analogy, because a sound wave actually represents the sound. And this in no way represents the light that we're representing. It is purely color data. We just have numbers of each color and we add them together, and it happens to look that way when we draw it out, but it does not actually represent the light. It only represents the color data as a mathematical equation. But the JSON color data is going to look like this. That's why we had some of those repetitive parts. So something like this great deep trough over here, or one of these really high crests, it's going to repeat a lot. But in general, it's like a sound wave. It's bouncing back and forth very quickly, so we get small segments of repetition and inconsistency in that repetition that we saw in that file. This is also why we can't change the size of a JPEG. So a bitmap, we can scale that down and we don't lose any clarity. But a JPEG, if we change the size at all, it gets very blurry very quick. You've ever seen that? Had that happen? You have a JPEG and it doesn't quite fit in your Word document, so you go try to change it a little bit, and then suddenly it looks awful. We have to have special software that can recalculate that discrete cosine transform. And redo all of that color data. That's why JPEGs, we can't get bigger or smaller. Or if we change it at all, we lose clarity. Change the aspect ratio even a little. Anything throws this wave off. But as far as clarity, you can think of like sound. This would make a good comparison to sound as a wave. Think about different sounds like the traditional robot sound, right? The scratchy one. It's like the original Battlestar Galactica series, the Cylons there, versus what our phone assistant software sounds like these days. What has it been? It's been like 2 years since Google ran that big thing, and their Google Assistant was consistently tricking a human into thinking it was they were talking to a human, not a machine. This is when they added in the sighs and grunts, and it started to seem annoyed, and would change its tone. Then it would almost always trick a human into thinking they were talking to a human, not to a machine. It's really funny when it first came out, but it's kind of normal now, 2.5 years later. But that high quality of sound, we can translate that back to images. So here's that traditional scratchy electronic discrete robot sounding voice. It's like a bitmap where it only has so many things it can use versus the entire spectrum. You just have to have special software if you want to make any adjustments and things like that. Okay, I filled up the board pretty quick. So okay if I erase the board? But again, this is just because it's not covered anywhere. When you're using things, I guess that would be the application of it. If you're looking for an image and you know you're going to have to stretch it out or change the size, somehow change it for what you're doing. And there's several different formats to choose from. You probably wouldn't want to choose the JPEG. That's going to get blurry when you go messing with it. If you do anything to keep it in the original size, or send it to a professional artist that has a really high quality MacBook and the high-end software to edit a JPEG and recalculate that. Which, by the way, that is the difference. There is a graphical difference between Macs and the other systems. Because so this time my grid is the grid is pixels. The pixels on our screen. And Linux and Windows will use floating point numbers and approximate that. So we might have a dot here and dot here, here. And Windows and Linux, if it's created on a Windows or Linux machine, it's going to use those floating point numbers and then round them to figure out what the nearest line is, which can cause a problem because, let me move this one over a little bit. Maybe the machine we think it's on moves this dot we created on a machine that moves it over to this line, and it looks like we have a straight line when we created it. But then we open it up on another machine. That other machine thinks this one should be on this over on this pixel, so it rounds it differently. So that's created on a Windows or a Linux machine. But if we create it on a Mac only uses the whole numbers. So the only options of where to put those to control those pixels are directly on the grid. There's no rounding. So a straight line on a Mac really is a straight line. This takes a lot more resources. And that is also what forces Macs to have bigger equipment. It forces Mac to they have to have more processing power. And as a result of that, Macs have more processing power for the things that don't need more processing power. So it carries over in other stuff, but that is really the significant difference. Other than that, and everything else is just a byproduct of that because Macs have to have more processing power. But for artists, a straight line really is a straight line drawn on there. It's gotten better. They added things in with notes and stuff, so it's not as bad as it was 20 years ago. But it still does happen sometimes. Cool. we'll draw a picture, look really good on our Windows machine, and email it to our friends, and they'll open it up, and there'll be some fuzzy edges and stuff. It's still not as bad as it used to be, but it still does happen occasionally. Those are both big. There's a lot of information to store every single pixel by pixel piece of data. And then that big huge wave Fourier transform. Oh, I had a note here. Oh, that's about this. Yeah, it looks like a sound wave, but a sound wave really is an actual representation of the sound. That is not a representation of the light. It's just the numbers of the numerical representation of the colors that we put in that format. So it's also stored as an equation. So it loads quicker too. This, we have all these little steps. Has to carry out every single step. But for JPEG, since it's already erased here, but that wave it's stored as an equation. So to load it in, the computer just has to calculate that equation. And computers are really, really quick at that. So JPEGs also load faster. That may be another place where you might want to take into consideration. That made a big difference back in like the 1990s with the internet, transmitted across the internet, and translate all those pixel by pixel instructions, or translate an equation that can be recalculated. One of those is like way quicker than the others. Long before you all's time, but it still does, speed does still show up sometimes. Next on my list, I have graphics interchange format. So this one came about in the 90s as a result of that thing I was just talking about. JPEGs would load quicker. There's just an equation that we were trying to transmit. So that transmitted a lot better when everything was moving at 56 kilobits per second on the phone line. But we ended up with those scaling problems because everybody has different size screens. And different aspect ratios on the screens, things like that. So there were scaling problems. So I wanted to do something like a bitmap where we had a little bit of scaling control. And they also distort differently too, right? If we stretch out a bitmap, it pixelates. Whereas if we stretch out a JPEG, it gets blurry. Different types of distortion. So pixelation is a little bit easier to deal with. People decided that. So what are some advantages of that? But the bitmap was too big. So what they did is a special type of bitmap. And those original reasons are not at all why we still use them. They were replaced by something better, but there's another reason why we still use those. That defines its own color space. There's a lot of possible colors, right? Especially if we're talking about what the computer can handle. Colors are represented by 2 hexadecimal digits, usually, so 16 bits of red, 16 bits of blue, and 16 bits of green. There's a lot of ways we can mix those. Yeah, huge numbers, right? We have 16 bits for each one, 256 values of each, and we can mix and match them in any combination. It adds up to a lot of combinations that we can add transparency and stuff. That's a different point, but a lot of possible colors, and that was part of what was taking up so much space, is all of the color data. So they just cut that down. So draw this picture here to represent the set of all colors, every possible combination of them. It's like, okay, when we go to save that, it looks at the data we have. Computer will look at that data we have, and it's like, okay, I don't need every possible color. So it just makes a small subset. just use these. That's what I put in my notes. And then it's only going to use these colors. So we cut down our data size to just the part we need. That cuts out a lot of space. It was very, very quickly replaced with things. That's the next one on the line. So it would have gone completely out of format, except there are a couple other little tricks with the bits, kind of almost like compression things, where we look for those repeating patterns. And instead of typing out the repeating pattern twice, we just make a note, oh, this pattern repeats. And sort of what would basic compression algorithms included. So we end up with a really, really small file size. But it was restricted and it was replaced almost immediately by pings back when it was invented. About 20 years afterwards, 15, 20 years afterwards, somebody came up with ask an interesting question. It's where we learn stuff, right? Ask a question, look for the answer. You know, remember talking about the scientific method back at the beginning of the semester? Somebody asked a question, and when they looked for the answer, they got a really good one. Like, okay, this is way, way smaller than all our other file formats. We don't need to worry about the 56 kilobit per second transmission of phone lines anymore. If anybody's still using that, well, there's too few people still using that to worry about. So we don't necessarily need the small size. We can use the big fancy pictures. This is so much smaller. We could store like 10 or 15 of these and the same size as the typical image. And the answer to that question quickly led them to realize that means we could put an animation in what should be a still image format. I think that's what you all are familiar with GIFs, right? It would look really weird if you saw a GIF that only had a single image, because they're so much smaller. If it's 25 times smaller, then we can put 25 images there. And if they're slightly different, then we have an animation all into one thing. So that caused them to make a big comeback. Being able to, because it's still, when we do that, it's still like one frame of an animation, or it'd be like one frame of a video size still. So that one really paid off, and otherwise that format would have completely disappeared on us. But all the things we needed to be small back when we transmitted data across the phone line, it didn't apply anymore, but it worked out perfectly to just store small animations. Y'all probably know the limit on that, right? We get about half second. 1 second is a really big GIF. But a half-second animation that loops over and over and over again is oftentimes quite enough. A lot better than a still image. Back whenever it was created, though, the original version of it, portable, was almost immediately replaced by portable network graphics. These were designed from the ground up for speedy transfer, like the name implies. Intended for rapid transfer across networks. So this would have been mid-90s, I guess. It was probably being researched a little bit before then. But by then the world had settled into TCP IP protocols. You remember talking about those earlier in the semester? IP chooses the best route. TCP breaks our data down into independent packets. And then with IP, every packet finds its own individual route through the network. So instead of keeping all our data together, there's still a shadow of the bitmap like that, or that big wave where we can't really break it up. All of those instructions for each pixel that kind of need to put back together in the same order. What if we just think about the TCP protocol modeled for TCP. What if we just think about the TCP protocol to begin with and design our data format to be specifically broken down into packets and transmitted independently across the network into chunks? Let's see, image data. Notice it's not just color data this time. Actually writing image data is described in chunks. Which is the actual name for it. And in particular, those chunks are either going to be critical or ancillary. And I assume everybody knows what the word critical means. You might know what ancillary is, but it's the antonym of critical. This one is absolutely important. This one we can go without. So it goes perfectly with TCP/IP because when things get lost, some of our data is important. We can't put our image back without certain things, but then other things we can say, if this gets lost, ignore it. It's not important enough to worry about. And then pixels. Then pixels are grouped into layers. Which reference chunks. And who applied it. So it was something very subtle back here in the format. Which one was the theme? So if we look at the bitmap format again, this is a big repetitive section, but the repetitive sections are different sizes. If we look at the GIF, that just kind of looks like randomness here. Not much we can tell there. And the JPEG, we were seeing the different sizes repeating things. But you'll notice the different sections. There's not really any section here. The section is sectioned by how it repeats in the bitmap. And a GIF or GIF, however you want to pronounce it, is actually this the same way. It just doesn't look like it when we open it in text editor. Here, once we know it's a wave in the JPEG, we can kind of see the repetition of the wave, but we have some really small pieces, and then we have some really big pieces, and it's a mix of both. But when we get to pings, I'm going to try it. Actually, okay, so yeah. So the image data starts here, and we have about 2.5 lines, and the size my window is right now. And then in the next one, we have about 1.5 lines. And the next one, we have less than a line, but then we're back to 1.5 lines. And if we look through here, almost all of our data is going to be somewhere between, almost all of it's going to be about 2.5 lines. We might have some that are longer. This one's highlighted as about 3.5 lines, but it's all going to be around 2.5 lines, unless we hit spots that we didn't need. So it's sized for the TCP protocol. We can kind of see it there, but it's just random gibberish when we try to open it in a text editor, but we can get hints of that pattern. So that picture that we drew earlier, we have a few things. So our image data, we have things like grayscale. We're on one end of the scale, it's completely dark, and it spreads out, and at the other end it's very light. So how light or dark is it? Then we'd have some red information,
some green information, some blue information, and some position data. Throw that out to about the size. I could, I'm gonna put these words in here, inside the box. Red, green, blue. So it would actually be kind of like a scale like this, where we go from 0 to 255 and just choose a number somewhere on that scale. And then we have position where we have X and Y coordinates. And then our layers, so that's the image data. And the layers, well, we have a circle that is way over here on the bright side of the scale. This one I was thinking about the sun. I'll start with the sun. So yellow. Yellow is an even mix of green and red. If you didn't know that, RGB mixes an even mix of green and red is yellow, and then you add blue to get the tinting for it. So I'm going to skip the blue one, and then it references position data somewhere like right around here. So it's just a bunch of pointers kept in small chunks that are already designed specifically for the TCP protocol and labeled as whether they're important or not, so that if we lose any of the data in transmission, we can just go ahead and ignore it. Like, no, we don't need that part, or we absolutely need that part. It needs to be retransmitted. And optimize, it's built around the protocols we use for a network. Then we'd have another layer, looks something like this. The hole cut out, and then that one's going to point to the blue, so that's the sky from that picture. And this hole cut out, that's an important thing. We can have emptiness in it. So we're allowed to have transparency in those. Which bitmaps we can't have transparency, JPEGs we can't have transparency, because that would just be we can't leave a gap in that wave. We can't have a null value pixel, because if we turn the best we could do is tell the pixel to turn off. But when we restrict things, we can leave empty, we can remove some colors. We're removing things, so we actually remove some of those pixels data, and then the computer just doesn't know what to do, so it shows whatever's behind them. So we can have transparency in these two, and with pings, it's actual transparency. We have a hole in our layer. And if there's a hole in every layer, then we can see through all the way to the background, whatever's behind it. Then we'd have like a green layer. Because it doesn't have to be connected. So we have like the top of the tree and the grass. Those point to the green layer. Oh yeah. This would also make a reference up here to pixel 0, 0. It's like X, Y in your math. X increases as we go from math class. X increases as we go to the right, but the Y increases as we go down. So X is like math fast, but Y is the opposite. Like lines on a page, or in physics, down is a much better direction to put the positive, because things go that way on their own. Right? If I let go of this piece of paper, it goes down, not up. So down is a much better direction to make our positive, because that's what happens. That's what happens naturally, and it takes effort to go back up. Or really, it's like lines on a page. That's a good way to think about it. And our green, I guess if we pull off this point, the top of the tree is somewhere right around there. So we have these references. So here's our actual data. Then we set up some shapes, and then those shapes have references to the actual data, so that we can assemble it back on the other side. And then a little brown square that kind of mixes those and puts in the right position. But that's what a ping is. So it's designed to fit that protocol from the beginning. Again, good for transfer. But they're all locked in place. Y'all probably seen on pings. Give scale like bitmaps, we can go down, but when we try to go up, it gets pixelated. And if we go down and then back up, it gets even more pixelated. Because if we go down, we can just drop every other row and column like we did on bitmap, and it still seems clear. But if we try to scale it up after scaling it down, then we're missing half of our pixel data. So it gets even more pixelated. Pings we can stretch a little, both directions. We can go a little up, we can go quite a bit down and keep clarity. Because what we're doing is changing the size of our layer. We just change the size of our layer, all of our layers by the same ratio. So really it's just sending another ratio. And it's like, okay, scale everything down by this much, or scale everything up by this much. And we can do quite a bit until our corners start to get blurred. Where things come together, eventually we run out of, it scales up too much. And if we had a spot where two squares come together, we can only scale that up so much before we hit the space in between. The space in between them becomes visible, which hopefully matches what you all have seen when you change the size of a ping image, right? Or a bitmap or a GIF or a JPEG. There's reasons for all of it. That's how we do those. Any questions about pings, GIFs? Okay, if I erase the board. There's two more I want to put up here. Actually, there's one more, but we use two different human readable forms for it. It's kind of the same thing. And, you know, I guess the image we've been using for everything so far, and for one more, for the 2D version, doesn't really have a 3D equivalent. So I don't know if we can, I'll have to do another one to show the format for that and how to make sense of the format, because at least one person in here I know is going to do something that will require coding things in the format. So at least one person will need the next one as far as using. So the next one's scalable vector graphics. So .svg. Really, it's vector graphics internally to the machine. 2D vector graphics and 3D vector graphics are handled exactly the same internally to the machine, but we put them in different human readable formats. So really, this is human readable 2D vector graphics. And the idea is the image is stored, as points, lines, curves, let me take out the as there and put a color. The image storage, that'll make it. I apparently have a very grammatically incorrect sentence in my notes. Should have read that before copying exactly. So the image storage is points, lines, and curves stored as an equation. So like the name here, scalable. We can go up and down to any size and we never lose clarity because it's an equation. If we scale it up 1,000 times bigger, all we do is recalculate that to be 1,000 times bigger. Scale it down 300 times smaller, we just recalculate it to fit that size. Has everybody had like an algebra class? At least intermediate algebra, seeing with graphing and things. So this image, this one, I'll just draw up here and say we have a bunch of blue points. Then over here, somewhere we have a yellow x squared plus y squared equals r squared. That's the equation of a circle if you haven't seen it. Probably looks a lot like the Pythagorean theorem. It's exactly the same as the Pythagorean theorem, only if we think about every possible right triangle with the same length of hypotenuse, eventually it kind of comes around and makes a circle. So Pythagorean theorem, like if you're familiar with, is the equation for a circle. So we store a circle and just say it's yellow. And then it doesn't matter how big, the computer recalculates that every time. So we never lose clarity as we go up and down. And it's a lot smaller because all we have is an equation. We can take a fill up big chunks of space by just a little bitty equation. Then we have a green circle over here. A green x squared plus y squared equals r squared. And down here, a green y equals mx plus b. Has everybody seen the equation for a line before? That one usually goes up pretty early. We just have a green line or a bunch of green lines to add up to a rectangle. And then in between them, I'll write it this way, brown, we have a y equals mx plus b, like a line forming that up. And then we just have a bunch of equations and small notes about what color those equations should be plotted in. And the computer just constantly replots that. And we use a markup language, the SVG markup language, to put it in human readable form. So that's what was going on in those. And I think it's going to be about 10 more minutes, which is about all I have for this evening. That's why we haven't got to our break yet. Is that okay with everybody? 10 more, yeah. So you can see, well, instead of a line, it has it as a rectangle. The fill color, no red, 80 in hexadecimal, so that's 8 times 16. Is whatever the green value is, and no blue for the color. Give it an ID so we can refer to it in code. So, Grace, since you're heading into game development, that's something that'll be important for you. We can refer to this in the code immediately and just change those equations as they're needed. Or an ellipse instead of a circle. They have a circle. There's not a circle button, but ellipse is like a circle is stretched out, maybe like an egg shape. There's a big formal math definition for it. But the computer knows the equation for an ellipse inside. X minus a. Yeah, it's kind of a mess. There's a couple fractions on both sides of the equations. Anybody that takes trigonometry class or analytic geometry, you'll see the equation for that. They'll drill it into your head. Anybody that takes calculus 3, they'll drill the 3-dimensional version into your head. But a messy equation, but the computer knows that, so we can just use the word ellipse to say we need that equation. Or same thing, we can just say a rectangle, and it knows the equations for those shapes, and then a little bit of other information. 3D vector graphics, internal to the machine, are sort of the same way as the machine, and it's actually closer to what 3D does. So 3D, did everybody do like connect the dot pictures when you were little kids? That's how it's stored. So I'll draw a triangle. So we have vertexes, which are points in space. Okay, so we have like some XY coordinate. And then on this one, V2, we have some XY coordinate that describes where that's at. for all of our points. B3 has this XY coordinate defining it. Then we can just connect those dots. So we connect our vertexes with edges. And whenever we get a fully enclosed shape, we can fill that in. And we call that a face. So obviously we can build up any size polygon. Triangles are just the easiest to draw on the board, obviously. So we only have 3 points, but we could have one with about 10,000 points. And then we just keep track of the points, and we can choose whether we want the edges or the faces. And the other one automatically comes along with it. If we keep track of face data, then it's obvious what edges there are. If we keep track of the edges, it's obvious which face goes in there. So we end up with all the information stored that way. Let me just open Blender real quick and put a shape out there so we can see stuff. A cube will probably work. I'll just do a cube. That's probably readable. So I take this cube and export that file. Export as a wavefront. There it is. Oh wait, before I do that, I'm going to add a material. 3D is a little bit different. We can't choose a color because we have lighting and all sorts of stuff like that. So we have to give it a material that zoom stuff's in the way. Make a new material. And color is one of the things, but then we have other things that we would define off of it. Oh. So like give it some dark green color, but color is not enough on its own. We'd also need what's that color sitting on top of? Is it metallic? Is it rough or smooth? How does it reflect light? And we need all of that information too. Yeah, color is not enough for the 3D one. You'll notice right up here, there's a little light bulb picture that we have to take into consideration, and it'll do the shadows and all that. But we need a little bit more information for that. So let me save this. Save it as a cube. And if I go to export that, there's lots of different formats, lots and lots and lots of different ones. Wavefront I'm going to use wavefront. Create object. So I come over here. It created 2 files. So let me open those up in a text editor. I went with those because they're both human readable. And this time I can use my good text editor. I can't use my good text editor earlier because I have Sublime now, and Sublime can show images. So Sublime will recognize the pings and JPEGs and GIFs, and it will just display them in there. So I had to use the more basic text editor. I guess it is cheaper. It comes with the installation of Windows, so. But the more basic one. So if I open up both of these, we have cube.mtl and cube.obj. So MTL is the material that I put on there, which these abbreviations might look strange because this was not done by an American. We're so used to seeing American acronyms. These are French acronyms, so if you speak French, you probably know what those mean. I always have to look it up if I need them. I think KD is our RGB. But yeah, one of the few times that it wasn't done by somebody that spoke English. So if you speak French, the acronyms there probably make sense, but this is all the information to recreate that material. I believe NI is metallic as well, but I don't speak French, so I have to look those up every time I need it.
The big one here is the OBJ. So we have all of this data. So 1, 1, -1. Let's say, and there's a vertex, those XYZ coordinates. So X +1, X -1, 1, 1, 1. So over here, looks like positive Y is going off that direction. So positive X, positive Y. So over here and then down. So that's this corner way down here. And then we have another vertex at X, 1 of X, -1 Y, -1 Z. And this is just a cube, so we just have the 6 vertexes. And we'll skip over VP and Bennett for now. VN is normal. Normal is the direction straight out from it. So like a wall. Normal to the wall is the perfectly straight out direction. Very important for the faces when we put that in. And then we have F. So really what we need is the V's, the VT and the normal is kind of important. Then it says to use that material we created. And then we get down to the F's, so the faces, so we just have vertex and face, and then the edge can be figured out from the base data. 1, 1, 1. So that's saying we're going to start vertex 1. Those 3 sets of numbers relate to the things up here. Notice we have 3 different things. We have V, VP, and VN. So 1, 1, 1 is the first of each one. So that's vertex 1, vertex transform 1, and vertex normal 1. So we take that information and we connect it to 5, 2, 1. So there's a connection between that first vertex. So really we just need the first number here, right? So vertex number 1 connects to vertex number 5, vertex number 7, and vertex number 3. So that's 4 points. That's one of the squares that makes up the sides of our cube. So then we put those together, and then that gives us a face. And then notice the normal direction is 1. So then this says what is straight outward from that particular face. That's how that information goes. I spend a little more time on that than I normally do in this class, because there is somebody heading towards game development, and we'll need to know how to code that. And it's the text file. You know how to read the text file. So read the text file, bring that in. If you work in a Pygame, you have to code this information in directly. Pygame knows how to read it. You just have to tell it what angle you're looking at these things, which isn't really that much coding, but good practice if you're at some point. There's probably more interesting things to do along the way. But that's how we interpret that. I also happen to have one here. I'm going to do another one. If I go over to GitHub, I have starter points, so I don't have to start from scratch, or so that it's on GitHub so that any artist doesn't have to start from scratch. I spend a lot of time going with measurements to look at the picture. So like an elephant, I believe that's an African elephant. You can tell it's a lot smaller than an Indian elephant because of how it's, even at the angle, how it stands next to the human. A Siberian tiger, a gray wolf, a green iguana, an eastern hare, eastern box turtle, a western bullfrog. That's not the right name of. It's eastern bullfrog, and then the ones that live in western half of the U.S. have a different name. They didn't. They had to make it complicated, but I spent a lot of time finding all the different correct proportions to get starting points for those. And I happen to have the human one here as a Python script. So that same information here in Python format, view it all, and download that. Wait, there's a download button here, isn't there? Download. Oh. Blender. This. Zoom thumbnails on my way. And over here, if I open that file that I just downloaded, there's more than one way we can do it. So over on GitHub, if you looked a second ago, there was a lot of stuff, but here the line breaks are word wrap is turned off, so the line just goes a long, long ways off the screen. But we have these vectors. So there's vector number 0 here. It's Python, it's a Python list. So the first one is, there's our 0.0, followed up by point number 1, 0.2, and so on. And if I turn word wrap on for a moment, where's word wrap? Yeah, so we have all these points. Point number 1, 0, 1, 2, 3, 4. Every point gets an index there, a number, so we can refer to that particular one. And then the same thing we just saw in a different format. In our first face is a polygon with 4 corners. Vertex number 912 connects to 884, 2, and 96. And we make the edges that would connect those and then fill that in with the face. So that's how that information is. And if anybody's in any game development and needs to actually program it at times, which you will for realism and things, usually you let the computer generate a lot of it and you just do little adjustments. Like if somebody got punched in the video game character got punched in the face, you want it to distort a little, right? You don't want it to look like punching that plastic thing that doesn't move. Graphics like that are important, and we can just do a little equation to adjust those. That's why I'm spending more time on this, because somebody is heading on that pathway. But that's how our data is handled for 3D vector graphics, and then the computer just fills in the rest. I delete this box over here and run this script. Whoops. Here. Okay. So it's half a human because humans are symmetric. So if storing the other half is an extra data, we can just tell the computer to just mirror that across there and get the other half. Little things like that. But then all those shapes and stuff, I will go ahead and yeah, we don't need to see that in the other form. The same format. We give all of our vertexes or points in space a number, which fits nicely into an array in our programming languages. And then we just refer to those indexes from that array for the ones we need to make a polygon and fill in the face or the edge. But we don't need to do both faces and edges. We can, the other one, whichever one we choose, the other one is obvious. And I did not type this. I drew that with a mouse and all sorts of fancy tools. And then I had a computer just list out the point, write the file. So not as much work as what it seems like, but that's how that image data is stored in the different formats and stuff. Not really covered anywhere in any of the curriculum, because when we use images, we just download the one we need and throw it in our Word document or our slide deck or whatever, right? But there are differences. I guess the place where it might show up is keep in mind why some things scale different, why some things transfer better than others. There were purposes for all the formats, and yeah, I don't know where everybody's heading in the future. Some of y'all might need that. Some of y'all may never see it again. Those last two ones, the vector graphics, one person in here will definitely need it. That's why I spent more time on those than I normally do, because they are entirely in human readable form because programmers do interact with those for game development. Anybody have any questions about those? Hopefully that was at least a little interesting, maybe answered some questions that were in your mind about why our images behave differently. Most people don't ever really need to know that. That's why it's not included anywhere, but since whenever we have time, I like to cover it somewhere. Okay, I assume the silence means no questions. A reminder, final exam this week, and remember, final exams do not follow the same schedule as the homework. Final exams are on a calendar schedule, which means it's due Saturday, not Sunday. Otherwise, everything is due Sunday. This is the last day of the semester. The deadline that was set years ago. So I never accept late work after the final deadline. Make sure you get me any past due homework or anything by 11:59 p.m. on Sunday. And remember, your test is on a calendar schedule. It is due 11:59 p.m. on Saturday. And I did not write multiple question banks. So the test is pulling from the same question banks as the weekly quizzes. So you have seen, there's not very many extra questions in there. So you have seen every question that's going to be on the final. You've already seen it before, but I haven't added a whole lot of extra questions there. So you've already seen all of them. Hopefully that'll make it easier. Just go through there. As always, I look back over it, even though I wrote that quiz. I'll go look back over it and try to look for wiggle room in the grading and stuff. But if there's no other questions, that'll be it for this evening. Hopefully you'll find that useful. I like to include it somewhere because it's not included anywhere and it's definitely relevant to computers. At least shows you the creativity that we can approach the same problem from. Right? Lots of different ways to store the same image data. Y'all have a good night. I'll see you Thursday.